Hello, today our topic is separability of norm spaces. We start with, as usual, with several definitions. We say what A is dense in B I forgot to say what both A and B are some sets in norm space. A is dense in B if B belongs to closure of A. It is our first form of this definition. Second one, for each element from B and each positive epsilon, we can find an element A from A such what distance between A and B, so norm of difference, is smaller than epsilon. In other words, each element of B can be approximated with element from A with any accuracy. And one more form of the same definition for each B from B. We can find the sequence from A such what this sequence converges to B. Now, of course, this is norm in X and convergence also in our space X. First, let's discuss what all these definitions give the same. What means B is a part of closure of A? If we recall what closure is a set of all limit points, it means what each point from B is a limit point for A. And what is limit point? In each neighborhood we can find an elements of A. So it's exactly what is written here. So for each element of B in each neighborhood of this element we can find an element from A. And last definition, B is a limit point if we can build a sequence in A convergent to B. So this is what is said here. So all these three forms of definition give the same thing. And one more. We say A is dense everywhere in X. Or everywhere dense in X, it doesn't matter. If closure of A coincides with X. So each element of X can be approximated with element of A with every accuracy. And I think now the last, but most important definition, norm space X with its norm is called separable norm space if exists countable and everywhere dense set. If we can find set A, what is countable, and everywhere dense. So once more, space is separable if we can find such set what is small enough to be countable but large enough to be everywhere dense. So if we can find such a set, our space is separable. If we cannot, it is not separable. So it is like completeness. It is a property, an attribute of a whole normed space. Some spaces are separable, some are not. Let's consider examples. Most simple but at the same time most important example, space of real numbers, and it is separable because we recently proved what rational numbers are countable, and surely they are also dense because each real number can be approximated by rational number with any accuracy. Space of d-dimensional vectors is also separable. No, just because we also proved what set of d-dimensional vectors with rational coordinates is also countable, and every vector from Rd can be approximated by this rational vector with any accuracy. Space of sequences for finite P is also separable. We will prove it on exercises. Next example is space of continuous functions. with norm equal to super absolute value. Let's prove what these space is also separable. It will take some efforts. Let us divide our split our segment AB into n parts. So A is x equal to x0, x1, x2, and so on. B is equal to xn. And all parts are equal and have a length of delta n b minus a divided to n. X 0 equal to a, x k is equal to x k minus 1 plus delta n for all k's from 1 to n. Let's first build a set an of piecewise linear functions would obtain rational values in our nodes, so in points xk. The functions get on rational values here. So let us just describe it. G belongs to an means what G from xk belongs to rational numbers for all k's from 0 to n, and J of x is equal to J of x k minus 1 plus J x k minus J x k minus 1 divided to delta n and multiplied to x minus x k minus 1. So it is, as you remember, formula for linear function what obtains a value j of from xk here and j from xk plus 1 here. And x here belongs to xk minus 1, xk, k is equal to 1 to n. So all functions what in our this network, in nodes of this network obtain rational values form this an. Clearly the an, no, each function is defined by its values in the nodes xk. So an is fully described by q n plus 1 dimensional vector. N plus 1 means n plus 1 nodes, and each function described by these values in these nodes. So an is countable. And we consider the union of all such sets an for all n. And as a union of countable family of countable sets, it is also countable. Let us consider some f. Okay. Start from here. Let us consider some function f from our space. As it is continuous on bounded segment, it is uniformly continuous, so according to Cantor theorem, and for each epsilon exists some positive number data such that f of x minus f of y smaller than epsilon divided to 5 if x minus y is smaller than delta. There is some number such that delta n equal to b minus a divided to n is smaller than delta. So delta is some given number. We can plot a segment here. The length of delta, and by dividing the segment A, B into sufficiently large number of small segments, the length of each divisions can be smaller than that. And we take this n and fix it, and let us define g from xk in order to make it sufficiently close to f from xk, and precisely make it closer than 1/5 of epsilon for each k from 0 to n. We can do it because each real number can be approximated with any accuracy by rational number. Okay, so let us consider one point in segment AB. Surely this point falls into some segment. So x, we assume that x belongs to this segment, and consider the absolute value of difference of f and g in this point x. First we subtract and then add the f in left end of our segment, and then we substitute g from x for its representation as a linear function. So it is j from k minus 1 minus x minus x k minus 1 so here is j from x, so nothing changed. We just subtracted and added f and substitute g from x and for its representation. Continue here. It's smaller or equal than sum of absolute values. So here in these brackets, we did nothing with g's, but subtracted and added f from xk and f from xk minus 1. First we noticed what denominator is smaller than denominator because x belongs to this segment and denominator this length, and in denominator is length of all this small segment. So we can write this is smaller than 1, smaller or equal, and this can be estimated by the sum of 3 absolute values. So first two relations we keep without change. So finally we have a sum of 5 complexes, and each complex is smaller than 1/5 of epsilon. Here, because of uniform continuity of f, here because of closure or closeness of G and F in one node. The same here. Here again because of uniform continuity, and here because once again of closeness of F and G. So all sum is smaller than epsilon. So finally, let me show you what happens graphically. First, we divided our segment into several nodes. So we have some function f represented by these graphs, and first we our division is small enough to make function f change not very much on each segment. And next we build the piecewise linear function g by finding the close values of g in the nodes. These values are rational but close to real values of function f, and then we build such piecewise constant function g. And our procedure allows us to prove what distance norm of difference between f and g is smaller than epsilon. And last example. our last example will be devoted to non-separable space. We will prove what L-infinity space of bounded sequences is non-separable. The proof of non-separability of this space is built on a set of, let's call it S, so-called binary sequences consisting of only ones and zeros. So infinite sequences, elements of the sequences can be only 1 or 0. This set is non-countable. It will be proved on the exercises. And if we take two different sequences from this set, the distance between these sequences can be easily estimated. We assumed what these sequences are non-equal means what at least in one coordinate they obtain, at least one coordinate obtain different values. So in one sequence it's 1 and another it's 0. So supremum of difference will be 1 because at least for one key this difference will be equal to 1. These sequences consisting of 0 and 1, they have a fixed distance between them if they are not equal. So if we consider a set of balls with a center of open ball, with centers in elements of S and radius 1 1/2. So we will denote this set by B. So if B1 and B2, two balls from B, and they are not equal, so it can be easily proved that they are not intersect. Intersection of B1 and B2 is empty set. So please do it. We will discuss it. Let's assume that there is a countable everywhere dense set. Each point, each element from S, can be approximated by element of A, and each element from B, can be approximated by element of B. So if we consider a set of give accuracy what we like. So if accuracy smaller, for example, than 1/2. So for each b from B, we can find an element A from A such what A belongs to B. So we have this set of balls. B. And each ball is populated by some element from A. Here, here, one, another, third one, and so on. So in each ball we can find an element from set A, and as balls do not intersect, so one element from A cannot belong to two balls simultaneously. So we have one-to-one correspondence between set of balls and some subset of everywhere dense set A. We fixed these elements what belong to ball. We choose one element from A what belongs to the ball and move them to this set. So it is the set of all these points. So we have one-to-one correspondence between non-countable set B and the subset of countable set. It's impossible. So our assumption what L or infinity is separable is wrong. And we cannot build everywhere dense set here to be also countable. That's all. Thank you.